All right, this is page 3 of the flip-flop lab, and you're being asked to analyze the circuit that you find on page 398 of your textbook. I've scanned that circuit and I put it into my Word document right over here to the right-hand side, and I've shifted the state table to the left and the state diagram to the left as well to give myself some space to work right there. So the first question it asks about this particular circuit is this a Mealy or Moore model circuit? To answer that question, we look at the definitions of a Moore model circuit, and we find out it is a Moore model circuit if the output Z depends upon the current state of the circuit, which means basically, does it depend upon the outputs of the flip-flops only? If it does, then it's a Moore model circuit. However, if the output Z depends upon not only the outputs of the flip-flops, but the input X, then it's called a Mealy model circuit. The best way to visualize the difference is to look at a circuit. The top one here is a Moore model circuit, and the bottom one is Mealy. You'll see that in the case of the Moore model circuit, Z only depends upon Q2 prime, the output of a flip-flop. If you follow this wire, it just goes back into a logic gate. So there's no X dependence here, at least directly for Z. However, you do find a more direct relationship between Z and the input X. If you just follow this X right here, it goes right in here, and it's basically an input into this AND gate, ANDing with Q1, and that goes to Z. So if we see that Z depends upon X through some kind of logic gate or even a direct wire, well, I guess you wouldn't really have it that way, but through a logic gate, then you're going to have a Mealy model circuit. Also, the state diagram should look different as well. For a Moore state diagram, because the output Z, which is the bottom number right here, does not depend upon what X is. That means that as we go from one state to the next, we actually put Z inside of that because it only depends upon the current state. Z only depends upon the current state in a Moore model circuit. In a Mealy model circuit, you have some X dependency. So you don't put Z inside of the state, you actually just put these two numbers which correspond to what state number it is, state 0, 1, 2, and 3. And then what you do is you have on the upper left-hand side of this slash is the value of X, and the value over here to the right-hand side is Z. So in this case, if X is equal to 1, Z is equal to 0, and if X is equal to 1, in this case, Z is equal to 0, and so forth. All right, so back over here to page 3. If we look at problem number 2, it says, or part number 2 rather, it gives us the equation for a general JK flip-flop. We're going to apply it to the specific circuit that we have here. So we have flip-flop 1 and flip-flop 2, so we're going to have Q1 star and Q2 star. I'm going to try to zoom in on this area and have my equations right below that, just so we can clearly see this on video. All right, so the first thing I have here is just the general equation for a JK flip-flop. Notice there's no subscripts 1 or 2s for the Qs. And also I'm going to need a subscript 1 and 2 for the JK flip-flops as well. So here you see I've added two equations, and I put 1 subscripts for all of these and 2 subscripts for all of those. So these are the next state equations for this flip-flop and that flip-flop right there. All right, so you can pause the video at any time you need to copy these equations onto your handout to help you get over to the next state table that's to the left. All right, so if you look at the input J into this flip-flop, you see that it's an AND gate, which is ANDing Q1 prime with X prime. So the equation for J1 is going to be equal to X prime and Q1 prime. And if you look at the input of K, and you trace it back over here, you see that it only depends upon Q2 prime. Now if you look at the input of J2, this second flip-flop right here, you're looking at an OR gate being fed into J, and it's ORing Q1 prime with X. And so that's what I have right here. And you also see that the output of this OR gate goes right into K as well. So I can just come over here, copy that equation in, then change this to K. So what does this do for us? Well, it allows us to figure out what terms go into this next state equation to help us build the state table and the state diagram. All right, so let me see if I can just do this in Word. What if I copied that generic next state equation for the first flip-flop, and now I do the solve and substitute. I take J1 and I put it in for J1 right there. I take K1 right there and I put it, okay, wait a minute. I got to make sure I prime it. So if I look at K1 prime, it's actually going to be this with the prime on the outside of it. So if I do that, I see that I got a double prime, and that means I can just take those away for simplification purposes. All right, and I'm going to do the same thing for Q2. I'm using a solve and substitute approach. Probably should put some parentheses in there, like here, open and close parentheses around that, and then open and close parentheses around this. You see that I did leave the prime on there for the K2 prime. All right, now let's see how we can use these next state equations for Q1 and Q2, Q1 star and Q2 star, to fill out the next state table, or it's just called the state table. So let's look at, for example, Q1 star. And I'll put some underlines in here to show where the numbers are going to go. So this is Q1 and Q2, Q1, Q2, etc. for x equals 0. And then this column of two numbers, zeros and ones, corresponds to Q1 star and Q2 star for x equals 1. So x equals 0 and x equals 1, and the output is z over here. Now the output z should be fairly straightforward, because what you can do is just come up with an equation of z, and you can just write that on your own right over here. You can see that it depends upon Q1 and Q2, but not the next state. It just depends upon the present state. So it only depends upon this right here, and that should be fairly easy to fill out. In fact, maybe it's the first thing to do. But let me help you fill out this one column right here of 4 zeros and ones. So what we want to do is look at the Q1 star equation over here and consider the case where x is equal to 1 right there. So then if I rewrite that equation and I say let x equals, oh, I said 1, I'm sorry. I'll let x equals 0 for this column right here, x equals 0. And if we say 0 with a naught on it, then that just corresponds to 1. And then 1 ended with anything else is just, well, the anything else. So then we say, well, what does this mean? Well, you'll notice that these two things are identical. So anything and anything is just, the anything. So that means that the output, or the next state, Q1 star, is going to be on if Q1 is off. And that corresponds to right there and right there. So the next state is going to be 1 if the current state is 0. The other condition, the OR condition here, is if both of these are on. We see that occurs down here at the bottom, so we put a 1 right there. That means that the only thing that's left over is something we don't include, and that's just the 0. By not including it, I mean that it's the output is only high if this is true or that is true. Otherwise, the output is 0. Now I'm going to get you started on filling out the Q2 star, which is going to go right here. Now what you can do, by the way, to handle the Q1 star on this side is to just rewrite this equation right here and now assume that x is equal to 1 instead for filling out this column. But let's look at Q2. So I'm going to do these four for you, and then I'll let you handle those right there. So we want to look at the case where x equals 0, and we're looking at Q2 star. That was way over here. And for x equals 0, what we do is we say, let's let x equal 0 in that equation that's right there. So we put in a 0 right there and a 0 right there. You'll remember from Boolean algebra that if you OR 0 with the anything else, it's just the anything else. That means we can remove the parentheses like so. The same holds true right there for that. So 0 or anything else is just anything else. And then if we double prime it, it basically turns into this. That means that the output Q2 star, the next state of Q2, when x is equal to 0, is true if both of these are off or if they're both on. Those are the only conditions in which you would get a 1. If it was 1 right there or 1 right here. Otherwise, the output is 0. So how does this help you in analyzing the circuit? How does it help you make a state diagram sketch, for example. Well, if you call this state number 1, oh, sorry, I keep saying that. This needs to be state 0 because that's the, the decimal number 0. So here's state 0 right there. What state should it go to next if x is equal to 0? All right, well, if you look down here, you can see that it's going to go to state 3. So it went from 0 to state 3 if x is equal to 0. All right, so how would we indicate that on our state diagram? What we would do is say that there's an arrow going from state 0 to state 3, and this right here is x equals 0. So that's all symbolic there. This is Q1 and Q2, going from 0 to 1 in both of those cases. Now I'm going to let you decide whether this needs to be just 0 like that, or if you need to put a slash and then the value of z that goes right there. Now that's going to depend, as we mentioned earlier in this video, whether your diagram is a Moore circuit in which the value of z goes inside of the circle, or whether it needs to go on the way. So you have to answer that question before you determine whether the value of z goes here, underneath a slash, or whether it goes on this next line right there. Where does it go? I have to let you decide based on the type of circuit you have. After you finish your analysis of the circuit and completed the state diagram and the state table, you'll then build the circuit using JK flip-flops and these logic gates, and then show your lab instructor your working circuit and show how it goes from one state to the next. You'll want to use LEDs for Q1 and Q2. And then you can use another LED, say L3, LED number 3, for the output of Z. Your input X is just a switch, and of course you have the clock at 1 Hertz. So again, LED, LED, and LED for Q1, Q2, and Z.